Today's speaker is Dr. Keith Davis. He is an associate professor in the Department of Physics and Astronomy, and he is the director of this facility here, which is called the Digital Visualization Theater. And this space offers instructors the ability to immerse students and you in high-resolution images projected on a 50-foot diameter dome, which is right above you, 360 degrees. So you can really be immersed in the experience, whether it be like today, what Dr. Davis is going to show, or chemistry, or anything that professors would like to teach in 3 dimensions here. Whether people are studying geology or biology, biochemistry, physics, you can do it all in this room because it enhances the learning experience. Dr. Davis received his doctoral and master's degrees in physics from Clemson University and his bachelor's in applied mathematics from the University of Tulsa. Please join me in welcoming Dr. Keith Davis.
Well, good afternoon, everyone. As she said, my name is Professor Keith Davis, and I am the director here. That means that it is my job to work with our faculty to use this facility to teach our classes. However, I also get to use this space to share it with the general public, both visitors like many of you are today on campus, but also to school groups and others as well. We don't advertise a lot of that because I don't have the staff for doing as many shows as a lot of public planetariums do, but we are happy to share what we have with the rest of our local community, and so we do a lot of that as well. Now, my background is in astronomy and astrophysics, and as Tina mentioned earlier, we do presentations in here for classes that include things like biology, chemistry, biochemistry, physics obviously, astronomy obviously, art, design, theater, a whole range of things. It's just that if it's not something I'm an expert in, that's not something I teach. That's something I work with our faculty to develop what they need to be able to teach with, okay? So, you didn't come here today to look at me. You came here today to look at something really cool on the sky. So we'll move to that pretty quickly, but I do want to let you know a little about the major changes that we just made to the facility, because we're really excited about that. We've been pretty much the same technology that we had when we were absolutely state-of-the-art. I mean, in fact, so state-of-the-art that it was almost impossible in 2006. But we were pretty much the same as that until this summer. And we finally managed to do a renovation. We're very excited about it. So we have all new seats, which now have a push button lean back as opposed to a clunk clunk system. Those of you will remember that from before, that have been in here before. So that's very nice. We also have an entirely new dome panels. In fact, our new system is double the resolution we had before. The reason we got new panels is because some of the dim stars are so small now that they just fall through the holes of the panels. So we had to get new panels for that. We also have 10 brand new high graphics computers at the back that are running all the graphics, and 10 brand new projectors for much greater brightness, clarity, and resolution than we have had in the past. You can also actually tell that color stars are now the colors they're actually supposed to be, and I'm very excited about that. So can't wait to demonstrate it to you, and I think we'll go ahead and get started. So as I reminded you, please don't exit near the back, exit near the front. The other thing to keep in mind is that these are bright, and I need your eyes to be as adapted to the dark as possible. So please keep in mind that if you bring up your phone, it's going to glow. It's going to light up your face, and everybody's going to know who pulled their phone out. And the people sitting behind you will be perfectly lit up so that they can smack you on the back of the head and ask you to put your phone away. Please don't actually enact violence in my planetarium, please. But just as a joke, please keep in mind that we do need all lighting to be damped down, all right? Let's go ahead and get started. Now, I will be asking you questions during the presentation, but since I am seated in the back, it will be a little hard for me to hear you. So please be loud when I ask you questions. Also, turn your eyes back a little. Is everyone hearing me okay? I was adjusting my microphone earlier. Okay, good. All right, so what are we going to do? Let's go ahead and take the lights the rest of the way down. So tell me what you see. Yeah, if you look to your right, you can see the library. Our new system is pretty cool. It's actually allowed to connect to the internet. Our old one wasn't. And one of the things that's nice about that is we actually have the Google Tiles as an option, so we can really, I can really make it very, very clear that what I'm about to show you is the sky from South Bend. So we're going to start out here in South Bend, right exactly where this building is, just as though we'd magically removed the dome. What else do you see besides the library? The sun, right? The sun, of course, is our nearest star, nice and bright and outshining everybody else, simply because of its closeness, not as much because of how bright it is, or how bright what we would call its intrinsic brightness is not that much more than a lot of other stars. It's just much, 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 much closer to us than those are. So what I'm going to do now is speed up time a little. And as the Earth turns, we can see that from our perspective riding along with it, we see that the sun seems to move over to your right hand. So what direction, north, south, east, or west, must be at your right hand if the sun is moving that way? West, of course. And now as the sun starts to set, we can see it slowly darken. Now tell me what you see. Stars! Is this a lot of stars? Ah, I hear some older people saying absolutely not, while my young people say yes. That tells me some things. So, I have set the sky to be light polluted. Now, why would I do that? The whole point of having a planetarium is to get around that light pollution, right? Or a digital visualization theater, whatever. The reason that I'm doing it this way is because I like to at least take a moment to show people the sky and how to identify or find some things in the sky most of us see most of the time. Because even in light polluted skies, you can often find things. So this is set up pretty close to what it looks like in my backyard, and I live in South Bend, so this is pretty close. Does anyone know of anything? Can you recognize any shape or pattern of stars that you can see in the sky? Just shout it out if you think you do. Little Dipper. That should be behind you. That's the Big Dipper. Yeah, this is the Big Dipper. The Little Dipper would be over here. It's just in these light polluted skies, you can see the North Star, which is at the tail of the Little Dipper, and then the what is this? The two stars at the end of the Dipper part, but most of the stars in between are pretty hard to find. So that's the Little Dipper. Does anyone know what this shape is? Kindergarten answers are allowed. That is a triangle. That is a specific triangle that has a name. Does anyone know the name of that triangle? That's the summer triangle, exactly right. And the summer triangle is technically not a constellation. Now, every group of humans, every culture that we have ever been able to study has looked up in the sky and made patterns out of the things that they saw. So when I talk about the constellations, I am talking about the ones that are from Greek and Roman culture, because those are the ones that I was taught, and then the ones that have been added to over the years. But we don't consider, but for some of us, we don't consider this to be a constellation. We consider it to be an asterism, which is just a thing in the sky that we have a name to that isn't one of the official constellations. Now, if you call it a constellation in normal English, I'm not bothered by that at all, because there are lots of science words that mean different things in a science context and different things in a normal English context, and that's perfectly fine. So these three bright stars are Deneb, Altair, and Vega. And those three bright stars are from three separate constellations. Actually, let me go ahead and light up that summer triangle for you so you can see that. And now I want to talk about the constellations that they are a part of. So this one right here, this is Deneb. It is, do you see how there's kind of a cross of stars? Does anyone know the name of that? Just say it if you know it. That is Cygnus, exactly right. It is sometimes referred to as the Northern Cross because there is also a Southern Cross. But that's called Cygnus. Any idea what it's supposed to represent or what it usually represents? Yeah, a swan. Now, you could probably do just about any bird you wanted to. You could even turn it around if it's got a short body and a long tail, you could make that. But of course, we've got a nice swan, or I often think of it as a Canada goose because that's what I see more often around here. The next thing I'd like to do is bring you down here. This one's a little hard to see, especially with that bright. This is one of the great things about my new projectors is that if I show an image, it kind of outshines the stars, especially in this light polluted motion. So let's take that down for a second. If we come down here, do you see this bright star? And then, gosh, that's really hard to see. So what I'm going to do is after I've shown you this and Cygnus, I'm just going to go ahead and end that light pollution and make it a little easier to see what we want to see. Now, is this a lot of stars? Yeah. Now, if you have never seen a sky that looks like this, get thee outside in a dark place because this is beautiful. It's even more beautiful and more real in the legitimate and honest and real night sky. So I want to encourage you to do that. There is, in fact, if you didn't know, there's an International Dark Sky Association park that is just about 45 minutes drive away from here. So if you're local, you can head out to that park sometime. Look it up and find it. And that is an area where there are regulations about the lighting in the area to try to keep the light pollution low. But so to come down here to this constellation, now you can see there's a lot more to it. I like to see it. This is another bird. We've got the head of the bird. I imagine the eye, the beak, tuft of feathers sticking off of the back there. And then we've got two wings coming up like this. And then a tail coming down like that. That one is, does anyone know it? Say it if you know it. It is an eagle. And its name is Aquila. So let me bring up Aquila here. And almost all diagrams show it as a graduation cap with a tassel or something. I think everybody's like, why is that an eagle? And it's like, well, because if you don't draw this line and this line, then you get wings. But for whatever reason, most people draw it that way. Here is our artwork for that one. And now as we come up here, this is one that I think should be a bird, but isn't officially a bird. You've got a parallelogram right here. You've got, of course, that bright star Vega. And then you've got, I see this little thing as being kind of a beak. And this being the puffy chest of a duck that's not flying. Does anybody see a duck there? That one is Lyra. It is not supposed to be a duck. It is supposed to be a musical instrument known as a lyre, which is kind of a miniature harp thing. So there's our three constellations that are a part, or that have a bright star in the summer triangle. And you may notice that it's not summer anymore. So why can you still see the summer triangle? Well, it's named that way simply because that's when it tends to become visible. In early June, you will start to see it rising in the east just after sunset. And so most people notice things in the sky earlier in the evening because many of us like to just go ahead and go to bed rather than stay up and view the sky. So, what's this? That is the Milky Way, and the Milky Way is the galaxy that we are a part of. I'm going to go ahead and speed up time a touch because I want to show us some things later in the evening. So you'll see not only did the sun rise over to the west, move across the sky and set to the west, you can see, rise in the east and move across the sky and set to the west. You can see that the other stars are doing that as well. And so as we wait into the evening, you can imagine sitting outside and watching as the stars slowly resolve over hours. If you look to your left, there is probably the most well-known constellation in the northern hemisphere. What do you see there in the east? Orion, yes. So Orion is one of my favorite constellations, partly because everybody knows it. Also, these three bright stars are almost always visible even in light-polluted skies, not throughout the year, but in light-polluted skies they are. Let me go ahead and, did I prep properly to bring up the stick figure for Orion? I did not, but the nice thing is now I can just bring it up right quickly here. There we go. Now, Orion is often seen as lots of different things. In fact, I just saw a recent presentation where Orion and Pegasus were shown as other things in the sky for some of the Ojibwe and the Lakota cultures. I'm not going to tell you much about that because it's not my place to, but it was really exciting to finally get the chance to learn from other people about how they see the sky, so I think that's pretty cool. But we tend to see him as a hunter. Let's go ahead and bring up the artwork for that. Now, I want to start thinking about some of the other things that we can do with our system here. So as you look up at the sky, I am doing my best to represent it as it looks sort of to the naked eye in a very, very dark place. But we live in 2025 and we have an enormous amount of information about the sky that we have collected by telescopes. So I'd like to show you some of that now. This is a view of the sky as seen by many, 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 many telescope images and put together and referred to as the Digital Sky Survey. So this is not trying to look like what you could see with your eye, and you get to see a lot more. Of course, this is why you get this postage stamp view, is because this has been taken, when you take an image with a telescope, you don't look at the whole sky at once, you look at little squares of the sky, and so that's what you're seeing there. Now, what I want to point out is we had the belt of Orion, we had the shoulders, we had the feet, and we have that fuzzy blob. Does anybody know what that fuzzy blob is? It is a nebula. And now nebula is a term that in astronomy means fuzzy thing. Literally, it just means fuzzy thing. Anything that looks fuzzy in a telescope gets called nebula until we figure out what it is. Sometimes now we tend to think of nebulae as being gas or dust. So let me just take a moment here. I am going to switch over to a telescope view and zoom in on that, but I have to target it. Please be patient. I am still learning how to drive my fancy new car here. Where is my, this should do it, I think. So we're going to have a crosshairs and is going to track over to the Orion Nebula, also referred to as M42. M as in Messier, which is the person that put together the idea of a list of objects that were not comets. He was a comet hunter, and he kept getting annoyed by trying to chase the same thing. So he made a list of not comets. As we zoom in here, you're going to see a lot more detail appear. And in fact, I've added an extra special image on top of this. So now what do you see in that thing that we called the Orion Nebula? What do you think you're seeing there? It is gas and it is dust. The dark areas tend to be dusty regions, and the light areas are regions where light is being emitted. If you look at the center here, there are a handful, there's like a bright region and a handful of very bright stars that are very young and very, 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 very hot. And they are actually lighting up the rest of this nebula, this gas and dust, and making it glow. The dark patches, of course, are dust. Dust is not going to emit light in the visible range, and that's what you're seeing here. So this is a region in our own galaxy where new stars are being formed. There's been a lot of work done to study it, and I'd like to show you a view that has been put together at our best attempt to imagine what the three-dimensional structure of that nebula is. Now, it looks very different here because it is a different wavelength, and they've chosen different colors for it in this view. So as we zoom in, we have this, we've looked at the nebula and tried to build a three-dimensional structure. We see these tiny little blobs of dusty cocoons, and inside of there are new stars being born. So as we zoom in on one, again, this is an artist's rendition here. We're just going to show you what we imagine may be there. This is the disk surrounding around a baby star right in there, and it's shooting some material at the top and the bottom as material that could eventually become planets comes together. So that's just a view of what we believe is there, and some of that was based on trying to genuinely position where those where the objects that we find within it are. So it is based on data, but it is not exactly that. It is sort of an adjustment. What I'd like to do now, though, is ask the question, how on earth do we know that? How do we know that? How can we convince ourselves that when we look out at this fuzzy thing, we have some understanding of it as a 6 to 10 light year across object that is collapsing gas and dust and making solid stars within? Well, there's plenty of beautiful, exciting things I want to show you today, but I also want to tell you a little about how we know what we know. Because I think everything's just a little more believable when you have at least the beginnings of what we know. So as I zoom out here, I'm going to switch us back to our more realistic view of the sky. We'll take away that crosshairs. Now, as you look at Orion, take a look at this star here and this star down here. What do you notice about those two? Colorful. What color would you say this one is? Kind of orange. What color do you see for this one? Kind of yellow or blue. That you are already starting to do a little bit of astronomy. You're noticing something different in those two stars. For those of you that, though, maybe your eyes are kind of like mine, they're not the best anymore, if they don't quite look, I'm going to exaggerate the colors of all the stars here a little bit. So I'm just exaggerating this. No stars really look quite like this, but if I exaggerate it, we get a big difference in there. Now, what I want to do is talk to you about what that different color tells us about the star and how we know. And if you'll forgive me, I'd like to show you a graph real quick. I know some of you were deeply traumatized by science and math in high school and are bothered by graphs, but if you can hold off your hives for a moment, I think it will be helpful to show something. So, what I'm showing you here is a graph of the spectrum of an object that we call a black body object. Now, astronomers call it a black body because it is perfectly black, theoretically. It's not a real thing. We can't actually make these. But this is the idea of what would it be like for a perfectly absorbing object. And a perfectly absorbing object also has to be a perfect emitter. So as you warm an object up, it will start to glow. Every object that is not absolute zero temperature, and how many objects are absolute zero temperature? None. So every object glows, including you and me. We all glow because we're not at zero temperature. This is a graph of the color or wavelength of light, and you can see that there's the visible spectrum in here. So you would see light of about 450 nanometers as purple, and light with a wavelength of about 700 nanometers as very, very reddish, starting to get even hard to see up there. And this is a measure of the amount of light that this object gives off. Now, why am I talking about a black body? Stars are very, very good approximations to this. So when you look at this, you see, what do we see over here in the short wavelengths? Do we get any light from this object in the short wavelengths? No. And then what do we see? As I move to lower and lower wavelengths, it brightens quite quickly, actually. Where is its peak? Somewhere in the blue or green. And then it comes down again to this nice little tail. You can't see this tail, but I know that it continues off this way. Okay. Watch what happens. This is an object that's about 5,800 Kelvin, or about 6,100 Celsius, if you're used to that temperature. I think it's about 10,000 or so Fahrenheit. If I adjust the temperature to a lower temperature, what do you see about the light? Longer wavelength, which actually kind of paradoxically means short, less energy. So we get light of less energy if we're cooler. Does that make sense? Right? And we get less of this high energy light. Now, if I were to then brighten it up a little, get up to a temperature of maybe 20,000 degrees or 20,000 Kelvin or so, now we get a lot of light in this really short wavelength, high energy area. So what this does is allow us, if I go back and put a couple of these on the graph with different temperatures, we can compare them. We can see that objects of different temperatures produce different amounts of light in different wavelengths. Are you with me? Okay, what does this have to do with stars? This is one of the ways that we measure the temperatures of stars. Because remember, on Earth, the majority of information we get about the rest of the universe comes to us as light. And astronomers have gotten very, very good at understanding how light and matter interact. What kinds of configurations of matter make light? What kinds of configurations of matter will block light? And so on. And by looking at these different ways, we can measure the temperatures of things. So let's go ahead and go back over to this. This is an example of how we might try to measure the temperature of a star. You might imagine it's really hard to measure every single different wavelength. Does that make sense? So what we do instead is we stick filters in front of our telescopes of different colors, and we measure the total amount of light that comes in multiple different filters. So here's an example. Let's go for a really hot one. And consider you're going to get a lot more purple light than you do green light. And then if we go to a lower temperature, you still get a little more of this purple, but it's much closer than it was before. And if we go to a really low temperature, we're starting to get more red light than we have green and purple. Do you see what I mean? This is not completely different than the way your eye sees color. Congratulations, your eyes are stellar thermometers. They're not great stellar thermometers, but they can look at stars and know that one that looks blue to you is hotter than one that looks orange to you. And this is a big part of how we do that, is by knowing how hot glowing objects make light, by building tools and filters that can see in different wavelengths, and then by measuring that, we can measure the temperatures of these objects. The drum team is getting going. All right, let's go ahead, and what I'd like to do now is I am now going to take you on a little tour of the universe here. By the way, you've got Rigel down here, Betelgeuse up here. Betelgeuse is an older star. It's puffed up and is now very, very red. Its temperature is relatively cool. And then we've got Rigel down here. It's a lot bluer. It's much hotter. And you can tell that just by looking at the sky. Let's go ahead and return our colors back to a more realistic view. And now what I'm going to do is take us to this morning. Tomorrow morning, I mean. Because I'm about to take us on a super cool flight off into the universe. And it's more fun to leave during the daytime so we can see what's going on with Earth. Do you see that bright thing over there in the east? That really, really, really bright thing? Not the moon. Does anyone know what that is? That's Venus. Venus is sometimes the morning star and sometimes the evening star. And right now, it's in this morning star. So if you're driving to work in the morning and you see that crazy bright thing in the sky, that's what it is. It's just a planet orbiting around the sun in the perfect position to shine at us in the morning. All right, now keep in mind, I'm still learning to fly. Be nice. What we're going to do is we're going to slowly take ourselves off of the Earth here. We're going to tilt our camera down. Head off over campus here. You can see the river, the fields, all the houses. Downtown's right over there. We're heading that direction. And we're going to shift into magic spaceship mode. We're going to need a magic spaceship because we're going to really break some physical laws today. Don't tell Einstein. Now you may think, wait a minute, that Earth looks upside down. But we are now in space. Where's down? Kind of nowhere. You could define down as being towards the center of the object you are orbiting or nearby. That's a reasonable definition for down. But we can call it a north and a south, or I guess a north and a south. But that's sort of just something we've added on. As we fly away from our beautiful planet here. I'd like to take us, let's get that moon orbit on here so they can see where the moon is. What do you think about the size of the Earth and the moon there? Smaller than you might imagine, right? Definitely, the moon really is kind of far away compared to the size of the Earth and the moon themselves. Now, as we get further out, we're going to see them as, it's almost like they're getting bigger. They're not. We're just showing them brighter so that you can see them. What I'm going to do is I'm going to take us over to one of my favorite planets. We are going to head over to Jupiter today. And you may wonder, wait a minute, where is it? All I see is some bright stars. But of course, it's important to remember Jupiter looks like a star from Earth. Now, We're already breaking the laws. We're going about 4 times the speed of light right now. 20 times the speed of light. Roughly 150, 230 times the speed of light. And you're still getting bored on the way to Jupiter. Keep in mind that the solar system is really, 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 really big. We're going a lot slower than that now. I've slowed us down. We're not breaking any laws anymore. But the reason I tell you how fast we're going is so that you recognize that even in our own solar system, when we look out and see where a planet is in the sky, we're not seeing where it is, we're seeing where it was when the light left it. Now, Jupiter, of course, is one of my favorite planets because it is the most massive thing in the solar system, except for what? The sun, right. So the sun is the most massive thing. Jupiter is second. They are both made out of hydrogen and helium mostly. They both have some trace elements, but they're mostly hydrogen and helium. But Jupiter doesn't glow as hot or as bright because it doesn't have as much mass as the sun, and it never got squeezed enough to get hot enough to have fusion at its core. And that's the difference between it and a star. It has all the ingredients, just not quite enough of them. Now, as we fly around Jupiter here, I'm going to bring up some of its moons. So when Galileo first used a telescope to observe Jupiter, he saw 4 dots that seemed to hang out with Jupiter all the time. And those are the biggest inner moons of Jupiter, and we now still call them the Galilean moons. But ever since then, we have been finding more and more little rocks orbiting Jupiter. Now, I mentioned earlier about how we use different wavelengths of light to measure things like the temperature of objects, but we can really measure a lot of things. James Webb Space Telescope is the world's most advanced infrared camera, and it got a close-up of Jupiter, and I'd like to show you that now. You can see that it looks very, very different. Now, keep in mind, infrared is the kind of light that you and I are glowing in now. Can we see ourselves as glowing? No, our eyes can't see that kind of light. So we can't just show you it, just take a picture and then show it to you. What we have to do is take a picture and then decide what colors we're going to assign to the different wavelengths of light. So we have to kind of adjust it a little to make it visible. But you can see that the Jupiter looks so different. We see so much more beautiful detail in it. You can see that there's a glow at the poles from Jupiter there as well. So this is a big part of how we study things, by looking at different wavelengths of light, understanding how different configurations of matter make different kinds of light, and then trying to infer what must be there making that light. Let's see what the sun looks like. We'll go ahead and swing ourselves over to the sun. So the sun is basically a natural, gravitationally confined fusion reactor. And as we get closer to it here, zipping by the other planets, you can see that after many, many years of studying it, we've realized that it has spots on it sometimes. Another thing that Galileo observed and wrote about. But as I get closer in here, hopefully you will see that boiling? This is something that you can see with a telescope. Of course, you have to have a special filter in front of your telescope, otherwise you'll set things on fire, including your own eyes. So let's not do that. But if you have the proper filters, you can just barely see this with the naked eye. But it's much, much better with objects like the SOHO telescope, which takes a look, or observatory, which takes a look at the sun. Now, I did want to show you a little example, another example of a spectrum. This is a real image of the spectrum of the sun. So you can see here that we start out at infrared, which is black to our eye. Then we go this way until red, and then it loops and comes over this way into orange, and then to green. And do you see how green is the brightest color here? Kind of yellow, but there's a lot of green. And we actually now know that if you measure all of the light coming from the sun, it produces more green than anything else. So why doesn't the sun look green? It's because you're always getting all this other light too, and that blends together into what we call white once you add it all together. Now, you will notice something. We don't just see that cute little spectrum of the black body here, we also see these gaps in the spectrum. Now, is this a bad photograph, or are those really there? No, nobody came along and scratched into the photograph. That's really there. We now know that those are examples of atoms that are in between us and the sun, absorbing some of its light, and that's how we know what the sun is made out of, by looking to see what patterns of atoms absorbing light from it that we can see. Okay. Let's leave our solar system behind. So now we're really going faster than anybody's allowed to. 300 times the speed of light. A 100,000 times the speed of light. Let me get these labels off. Million times the speed of light. Do you see any other stars moving yet? Oh, there's one. 75 million times the speed of light. So Star Trek speeds are millions to as much as 1 billion times the speed of light as they zip around the galaxy. So as we start flying out here, we can now see that that stripe I showed you earlier as the Milky Way now takes its place as a three-dimensional object. Now there are lots of different ways to model the Milky Way. This one has a lot of arms. It's not my favorite version of the Milky Way. We may make some adjustments to it later. But you might imagine that being part of the Milky Way, we can only look at it from where we are. We can't get a camera out here to look back at it. So this is not a thing anybody can really see or take a picture of, but they study the Milky Way from inside of it and try to get a sense of what it looks like if we were outside of it, and that's what you're seeing now. Now, as we slowly coast on our way, keep in mind that it wasn't much more than about 100 years ago that this might have been, it was reasonable scientifically to believe that this was the entire universe. That there was one bright galaxy made of billions of stars, and that's it. The rest was an empty void. But now, as a result of a huge amount of work by many, many, many people, we now know the distances to many of those fuzzy things we saw in the sky turned out to be so far away that they are their own galaxies. Every dot that I am showing you, it's not an exact image, but it is at least a real galaxy in a real position as astronomers have found it to be. No one knew this was there until our telescopes revealed it to us. And our mathematics and our science and our really hard work figured out how to measure how far away these things were. So every dot that you're seeing here, or every fuzzy blob that you're seeing here, is a real galaxy. And as we fly out of that, I'll bring up another set of galaxies here. Now the colors here are artificial. They're just trying to show you. Oh, we lost one of the computers in the middle. I have somebody to yell at about that. This is an early show for us, right? We're just starting to, this is the shakedown cruise, right? Every once in a while on a shakedown cruise, you start to see things. So you are really getting a chance to see behind the scenes here. That's okay, we were just about done. It's unfortunate that it's one of the ones right in the middle. Let me see if I can, I'm gonna go ahead and tell 6 to reboot, and maybe it'll finish by the time we're done and I can finish the presentation here. So hopefully that'll get done. But on our way out there, you can see it restarting. I appreciate your sense of humor on this. So what you're seeing now, this butterfly view, is not real. What I'm showing you is what we call a selection effect. We, as scientists, we're only drawing what we have seen, and we can only look where we can look. And so that causes sometimes what's called a selection effect in science, and scientists know these very, very well. And so that gap is where our own Milky Way is. The Milky Way is a pancake. And if you want to look out of the pancake, you're not going to look along the thick part. You have to look out of the thin part. Thanks, Dell. You're really doing a good advertisement today. So we see the thin part there. And so you look out of the thin part, and what that does for you is reveal that there's a lot of the part of the universe you can't see, but that's okay, because we think it's pretty much the same everywhere. So thank you so much for your attendance today. We have a few minutes left in our hour. I am happy to answer questions. Yes, in the center.
How many moons have they decided for Jupiter now?
How many moons have they discovered for Jupiter? I don't memorize it because it changes too much. I believe the last I checked it was on the order of 90-something, but Saturn's winning because it has over 100. Well, yeah. So, yeah. Well, sure. It's got those rings, it's, you know. Although Jupiter has its rings too, they're just not quite as bright and ostentatious. Other questions?
Where's Pluto?
Where is Pluto? It's exactly the same place it always has been. The reason you're right. I just, when I clicked, it did planets and didn't bring in the minor planets, right? So I usually try to remember to show Pluto. You want me to talk about Pluto not being a planet anymore?
No, I just want to know where it was.
Oh, yeah. So if you noticed on the way out when I showed you the orbits of the planets, they were pretty flat, right? And they're very close to circles. They are not circles, but they're very close to circles. Pluto's orbit is very much not a circle. It looks like an ellipse, or that's a mathematical term for a special kind of oval. And it is also tilted to the plane of everybody else. Okay? So as we learned about the solar system, when we first found Pluto, we thought it was really the only thing out there that was like it. We're like, well, it makes more sense to call it a planet than it does to call it like an asteroid. And so they called it a planet. But then over the years, we've gotten better at finding these things, and now there are hundreds, if not thousands, of Pluto-like objects out there on very similar orbits, kind of off the plane of the ecliptic, much smaller bodies, and so on. And those sort of encouraged us that what we really needed was a new category, and Pluto should be sort of the first example of that, which is why scientists redefined it. However, one of the people responsible for redefining it, Owen Gingerich, did stand in this space and say, when I redefined it, I didn't understand that there's a difference between science definitions and cultural definitions. So if you want to call it a planet, you're more than welcome to. Other questions? Yes?
Why did all the moons of Jupiter make a donut and not a sphere?
Why did all the moons of Jupiter make a donut and not a sphere? That is an excellent question. So the inner moons were really in a flat plane. Did you notice that? That it was almost like there was a group of inner moons and a group of outer moons? So the inner moons probably formed with Jupiter. And so when stuff is being drawn together under gravity, it tends to turn into disks instead of blobs. And then planets, in the case of solar systems, or moons in the case of gas giants, form out of that. So we think those formed with it. But all those other ones, we think, were an object elsewhere in the solar system that just got too close to Jupiter and got stuck. But all of those objects came out of the solar system. So they were in pretty close to a flat plane. And then as they got close to Jupiter, maybe they got thrown a little bit up and a little bit down, but not all the way up to make a full sphere. Does that make sense? So they got a little knocked out of the flat area, but not so far as to be just random all over the place. And so they don't make a ball. Very, very observant question. Other questions? We'll do maybe one or two more, and then I'll let you guys get back to tailgating. Yes?
How did you even measure how far away these galaxies are?
Excellent question. How do you measure how far away things like galaxies are? So many different techniques. In fact, in astronomy, there is something that we refer to as the distance ladder. Okay? And so what you do is you measure the stuff that's closer, because that's easier, and then you learn things about that stuff that's close and develop new techniques to use those things to measure farther away things, and then you use new techniques from there to measure farther away things. So we don't just measure the distance for very far away things directly. We stack our way up to it, and we measure it with many different ways to make sure that it all gives the same answer. Because in science, we don't usually believe it if you measure it once and get one answer. We want to measure it a bunch of times and get the same answer. But to give you an example of some of those techniques, one of the first ways we figured out that an object like the Andromeda used to be called nebula, now called galaxy, we figured out it was about 2 million light years away. How did we do that? There is a special kind of star called a Cepheid variable. You actually are very familiar with one of those. It's the North Star. Cepheid variables, Cepheid means the first example was in the constellation Cepheus. Variable means its brightness varies. Okay? So these special kind of variable stars, they were studying them to try to figure out why and how they vary, and they realized that they brighten and dim on a very regular pattern. They brighten and dim, and brighten and dim, and very predictably. Then eventually, they figured out that by looking at a bunch of objects that were in the same space, they could kind of ignore how far away they were, and say, well, they're close enough to each other that we can just kind of pretend they're all at the same distance. So now we can compare their brightness, right? So what they said is, wait a minute, the ones that take longer to brighten and dim are brighter. And the ones that brighten and dim quicker are dimmer. So they had something that they could measure that it didn't depend how far away it was, right? We can measure that brightening and dimming without knowing how far away it is. Then we could look at how bright it seems to be, and then figure out how bright it must really be. Because if you think about it, when you look at something and see how bright it is, you're seeing three things. You're seeing how bright it really is, and how far away it is, and how bright it appears to you. And that's an equation that connects. If you can measure 2 parts, you can get the third. So they figured out a special kind of star that they could measure how bright it really is by this vibration, by this brightness change. And then by seeing how bright it appears to be, they could get the third one, which is how far away it is. That taught us the nearest galaxies. And then we've just developed new and new similar techniques over time to measure other things. So one of the ways we do that is we now have a good understanding of how the universe has been stretching over time. And so as the light has come to us, we've seen that it has been redshifted or stretched. We can now use that as a proxy for how far away the object is. So that's how we measure the distance. But we don't rely on that only. We use lots of different techniques. That was a very long answer to what seems like a very simple question. The thing I will tell you, though, is that the hardest thing astronomers do is figure out how far away something is. Because on Earth, if you want to figure out how far something away is, generally you take something you know the distance of and you lay it next to that object. We can't do that in space. That's really hard to do. OK, we'll do one final question that I'll make sure is very, very short. Any other questions? Yes.
How do we find out about more events that are open to the public here?
How do we find out about more events that are open to the public? Follow the College of Science events page in the College of Science social media. We always advertise our materials, our stuff there. In the future, if I manage to get the staff person I've been asking for, maybe we can do some email lists and stuff like that. Every time I try to start it, I realize it's been 3 months and I haven't done anything. So it's just a matter of my own bandwidth, right? But I do have very, very helpful people and an actual events team in the College of Science now. So they're very helpful and always make sure that my things are advertised. So subscribe to those social media accounts. Perfect ending question to a great day. Thank you all so much. I will be up at the front if you have further questions, and I am happy to keep answering questions for a long time.